We're going to look at the law of reflection, or basically any type of reflection that occurs when light travels from one medium and suddenly comes into an interface where the medium changes. Usually this changes the index of refraction, it changes the speed, and this leads to a reflected wave. So looking at this, again, a ray of light, let's say an incident light, will be traveling in a medium. It encounters a boundary with a second medium, and part or all of that incident ray is then reflected back. It essentially travels back into the medium from which it came. Very common instance of this is the case of a metal-coated mirror. The index of refraction of metal is actually quite complicated. In fact, it's complex. And suddenly we go from air to this metal where there's going to be about 95% reflection. It's going to be a little bit different for the angle of the light that comes on the surface is going to be reflected by the surface. Other examples include the surface of water, the surface of uncoated glass, anything that's going to change the index of refraction and suddenly make the light travel into a medium that has different properties from the medium from which it came. We're going to get a reflection. Now, how do these reflections take place? Well, it's quite complicated, but if we want to think of a very simple, if not overly simplified model, we can imagine a photon of light coming into contact with an atom. Essentially, a reflection is like an elastic collision, a collision where no energy is lost by the photon. It simply just changes its direction in which it's traveling. Okay, it retains all the energy that it had. Its momentum obviously changes because it's changing direction, but again, it is going to essentially be an elastic collision with the atom itself. Now, specular reflection is the type of reflection that we probably attribute to the word reflection. What do I mean by that? When we have a smooth interface, we are going to be able to take all the rays that are incident on that smooth interface, and essentially they're all going to be reflected at the same angle. This allows an object, in this case, you can clearly see these mountains in the distance, which are going to be reflected off the surface, producing an image, a nearly perfect image, which is inverted from the mountains that you see in the background. So specular reflection happens, again, whenever we have a very, very smooth surface. In fact, the smoothness of the surface has to be better, okay, smaller, in fact, of any defects, than the wavelength of light. Essentially, waves can see any change in the medium, which is approximately the size of the wavelength to anything larger. So even a small dust, which is bigger than the wavelength of light, and the wavelength of visible light is about half a micron, is going to affect the way that light reflects. Now, if you have bumps the size of an atom, well, an atom's much smaller. An atom is 10 to the negative 10 meters across, which is about a tenth of a nanometer, where light is about 500 nanometers for visible light. So slight changes in the distribution of the atoms on the surface, they're not going to really reflect, they're not going to really affect the specular reflection. But bigger bumps that are on the order of micron, will affect how the light is reflected. Now, diffuse reflection happens when we have a surface which has imperfections that are larger than the wavelength of light. And we see this on most surfaces. Most surfaces do not produce specular reflection. If you look on a surface and you can't see your image, well, it's a very good chance that you're seeing diffuse reflection where light is being scattered in all directions. It's still being reflected, but not in a way that's organized that's going to produce an image from this reflection. And here we can see in the first case, we can see light hitting the surface, bouncing all over the place in all different directions, and therefore we're not going to get an image. We'll see how images form in a little bit. On this surface here, it looks smooth, but in fact this laser light is hitting a frosted surface on this glass or on this plexiglass, and after it hits the surface, scatters off in all directions. So that's diffuse reflection. That's basically what we experience in most of our world. Defects, which are much larger than the wavelength of light. For instance, a painted wall, we have latex paint, which is typically made of small titanium dioxide particles with some type of dye in them to produce a color. Well, the particles themselves, although they're microscopic, we can't see them with our eyes, are large enough that they scatter the light in all different directions, and they're really appropriate for most rooms. We don't want mirrors on all the sides of the room because, well, that'd be quite distracting. Paper is an excellent medium for drawing, for printing text, even producing images, because it scatters all light in all directions. Since very few objects actually emit light, normally when you're looking around, you're seeing light which is reflected off of the surfaces of these objects. And again, most of this is diffuse reflection. Now, the law of reflection basically talks about how an incident ray of light, a light that is coming toward a new medium, is then reflected by the second medium. Okay, we say the angle of incidence represents the angle that the ray of light makes with respect to the normal. Now, normal is a mathematical term. Normal means that we have a line or a vector which is perpendicular to a surface. In this case, it's the reflective surface. So the angle of incidence right here is represented by this yellow arc, and there it's approximately 35, maybe 40 degrees, maybe almost 45 degrees, probably more like 40 degrees. Now, the law of reflection says whatever this angle is here, again, 40 degrees, the reflected light is going to be also that same angle, but in the other direction, for the angle of reflection is going to be equal to the angle of incidence. And again, we use the subscript I for incidence, we use a subscript R for reflection, and clearly you can see here that these two angles are going to be equal. Again, the incident ray is traveling in a different direction than the reflected ray. Here's a very nice example showing specular reflection off of a smooth surface, but also enhancing the view of the beam using smoke particles. Basically, this is an aerosol of either smoke, fog, or something that can be scattered by the laser light. Now, most of the laser light makes it through, so we can see the beam, the incident beam, striking the surface and then being reflected. And again, it's the law of reflection that's going to allow us to take an image like this top of the newspaper right here and invert the image as it's reflected off of the surface. Now, why do we coat most mirrors with metal? Well, simply because if we just used glass, and glass is a very nice surface because we can polish it, we can usually float it when it's being created, when we have plate glass that's being created, we naturally get a very, very smooth surface. Oftentimes, we don't even need to polish the surface. But really, when we look at the change in the medium, we go from air to glass. There is a fairly drastic change in the speed of the wave. There is a considerable change in the index of refraction, but it doesn't produce a very large reflection. Most of the wave still passes into the glass. So to really create an abrupt change, we coat the surface with a very thin layer of molecules. Typically, this is done in an evaporation chamber, and aluminum is one of the most common materials that we use. We only coat a few atoms thick, and this is more than enough to reflect all but about, I don't know, about 8% of the light. So again, the glass substrate provides a very smooth surface, can be polished to make it even more perfect. And then we coat this with a thin layer of metal atoms. In this case, if we're trying to create a bathroom mirror, we're going to coat it with something that's reflective in the visible part of the spectrum, and that's typically aluminum. If you remember the Webb Space Telescope, you probably remember the mirrors looking gold. Well, they look gold because they're coated with a very thin layer of gold. There, the substrate's a little bit different. Instead of using glass, they use a much lighter material, the element beryllium, polish that, and then coat it with gold because gold is reflective in the infrared where the Webb Space Telescope operates. Now, how does this work? How do we actually get a surface to reflect light? Why do metal surfaces reflect light so well? Well, metals have fixed positive ions surrounded by a sea of free electrons. Essentially, we've got a whole bunch of electrons that are almost free sitting on the surface of the metal. As the light comes in, we have this incident photon come in, or we have this incident wave of light coming in. It's going to cause the electron to vibrate up and down. And these vibrations are then going to cause a new wave to be reflected, the reflected wave, off in a direction where the angle of reflection is equal to the angle of incidence. So essentially, these free electrons are really, really good at undergoing, if you will, an elastic collision with the light. And as they do so, they basically send the incident photons off in the same angle, different direction, but same angle with respect to the normal of the incident ray. And again, here's just another view of this going on, the oscillating electron vibrating back and forth, and the incoming wave inducing these vibrations, which create an outgoing wave. Now, bathroom mirrors, dressing mirrors, just common everyday mirrors that you're going to use to, I don't know, get ready in the morning. These are typically coated on the back surface with metal. That means that the front surface is glass, and the glass will protect the metal coating on the back. And this is because, again, the metal coating is only a few atoms thick. That means it's very easy to scratch the coating off. So by putting it on the back side, when we clean the mirror, we're not rubbing up against this very delicate surface. In high precision optical equipment, they'll do the coating on the front side because the extra reflection from the front glass surface is not desirable. For you and I, just looking into a mirror, we barely notice this reflection from the glass interface. However, by putting the metal on the front side in a precision optical device, such as a telescope, the only reflection you have to worry about is that reflection off of the metal. So again, if we go back and we look at this, here we have the thin coating of metal on top of the glass. Again, this is very good for, let's say, a reflecting telescope. However, for your bathroom mirror, you would be looking through the polished glass substrate into the metal and then reflecting off of that metal. Again, the glass being a fairly durable material, and not so easy to scratch, not as soft as the metal, tends to protect the metal coating. Now let's take a look and see how a mirror produces an image. Basically, your eye is going to reconstruct where the rays came from. When we see an image, it's your brain processing where the light is propagating from or where it appears to propagate from. So again, we take a look and we're looking into the mirror, okay? What we see is the rays from our eyes are going to, the rays from the top of our head are going to be reflected at a fairly narrow angle because it's not much of an angle to our eyes. The reflection from the bottom of our body, from our feet, is going to travel at a steeper angle and then arrive at our eyes. Now, imagine if we take these rays and we work them backwards. This top ray right here, okay, let me just show this to you. I'm going to just draw this. This top ray right here, which is going to reflect off the mirror, if we see where it is appearing to come from, it appears to come from beyond where the mirror is. It appears to come from right here, where the top of our head appears to be in this image. Likewise, with the ray that came from our feet, it appears to be coming from this direction right here. So when our brain processes this information, what it actually says is, these rays are traveling in a straight line, and they actually came from this image that we see right here. Okay? And that's why we can see our own reflection. What we're actually seeing is not a real object. We are, in fact, the object. Rather, what we are seeing is the rays, the path of the light, and where our brain is reconstructing where that light, if it traveled in a straight line, where that light would have come from. So again, when we take a look at these images, again, it's an illusion. Our brain is doing a little bit of ray tracing right here, saying, okay, what I saw in my reflection, what appears to be coming from my reflection's head, actually bounced off the mirror from my own head. What appears to be coming from my reflection or my image's feet actually came off of my own feet. Again, we are the object. Our reflection is virtual. It doesn't really exist. It is our image. Now, what's interesting is we can get a house of mirrors type effect. If we have multiple mirrors, we can get as many reflections, depending on the geometry, as we want. Let's take this for example. Let's say that I have an object, and I'm going to take a look at this object and see exactly what happens when I place mirror A next to it. Again, when we take a look at this, we have a ray going from the top of the object, reflects off the mirror, and then comes back. It appears to come from image A. Same thing for the rest of it. A light ray from the bottom of the arrow bounces off the mirror. It appears to come from the bottom right here. So if I only have this mirror A right here, I'm going to get a single image. Now what happens when I add an additional mirror? Okay, not only do I have a mirror here, I have a mirror here. Well, I'm going to have the possibility of almost an infinite number of images. Really, the only thing that's keeping it from becoming an infinite number of images is every reflection is going to lose a little bit of light. So subsequent images are going to be dimmer and dimmer and dimmer. Okay, so let's keep track of everything that's going on right here. Now, I get my first image right here. Okay, my first image appears to be right here. So image A now becomes a new object for mirror B. Okay, and when I get a reflection there, that is going to create another image even further back. Likewise, I will have an image for B, which becomes an object for another reflection off of mirror A. That produces this new image right here. So I can have multiple reflections where an object creates an image. That image now becomes the object for another image, and the process can just keep going on and on and on. You can see that in this photograph right here. This person's standing in an elevator, a little bit on the creepy side because it's all different mirrors on all the sides. I guess it gives the illusion of more space. And you can see that this photographer is standing in the doorway, but yet they're the object. Their image is shown over and over and over again. And we notice that the image is getting less and less contrast. It's getting darker and darker and darker. And eventually it fades into blackness. And really, this is because all of these mirrors are acting as reflectors making one image the new object for the next image. Here's an example of two mirrors which are at a 90-degree angle with one another. And again, you'll have to excuse my drawing. I tried to do my best with this, but sometimes it doesn't come out as I would like. In any case, our object is going to make two images because of the two mirrors. The object is going to create an image to the right, and it's also going to create an image to the left. If I did this a little more carefully, I would have perfect 90-degree angles here. But what we notice is these images become objects for the next image. So this image A creates a new image here, or secondary image here, along with B, okay? So what do we see right here? We see a few different things. First of all, we see the first two images created, image A and image B. We also see that they create their own image within the system, okay? It's actually split on each side, but this image AB is actually the image from A and from B. Now, we can play another trick right here. We can change the angle once more and produce even more reflections. Now what happens if we set the angle, instead of at 90 degrees, we set it at 60 degrees. Here we got three images from one object. Now we set our mirror, okay, at that 60 degrees, and we're going to get 5 different images. And you can see if we keep changing the symmetry here, we could get even more images. If I placed it at a 30-degree angle, I would get a total of 11 images from one object. Basically, we will see as we get to more complex optical devices that when we create an image, if it's virtual or if it's real, that image can become the object for another image if our optics are set up that way. Here's another application of reflecting, an everyday application that we use all the time. It's known as a corner cube or cube reflector. If we create reflective surfaces at 90 degrees, just like the first case that we had before, we can send the second reflected ray the same direction or the opposite direction, 180 degrees from the way that it came in. Now, if you look at the if you look at the reflections that take place here, you can see the green ray is obvious. The green ray comes in, and then it reflects off of this 90 degrees, which is 45 degrees to this. So that reflection is going to be 45 degrees out, and then another 45 degrees, and we get the ray reflected back in the direction at which it came. But it actually works for just about any angle. Here it comes in a slightly sharper angle. But if we follow the rays, the angle of incidence equals the angle of reflection. Even though we're at less of an angle here, because of the 90 degrees, we have this complementary angle action going on here. The second reflection is going to be at a larger angle of incidence, and again, still send it off opposite to the direction that it came in. That means no matter what angle I shine light in here, I'm always going to send it back in the same direction that it came in. I can send it in at this direction. That's going to reflect off. Let me see if I can get everything right. And then it's going to come back in this direction right here. So it shines back no matter how we put the light into it. And what are the applications? Well, here's an application you probably are familiar with, a bike reflector. Bike reflectors are very effective at sending the light back in the direction from which it shines. So for instance, if a car were driving, it has its headlights on, the retroreflector, despite whatever angle these reflectors might be pointed, are always going to send the light back toward the headlights so the driver can see the bike. Another application was actually placed on the moon. This retroreflector allows us to actually measure the distance between the Earth and the Moon. It was left during the Apollo missions, and it's still up there today. Now, we can bounce a laser light off of this, and we can time how long it takes the pulse to go from the Earth to the Moon and back to the Earth. And in fact, this high degree of accuracy has allowed us to see that the Moon is moving ever slowly away from us due to the gravitational tidal interaction. So again, angle of incidence equals angle of reflection. It's a very simple rule. The law of reflection doesn't really take a tremendous amount of math to analyze.